Hello everyone, welcome to the ABB Process Performance webinar of Pushing Constraints in Mining with ABB Ability Expert Optimizer. This webinar will focus on the technology of advanced process control and how it brings value in terms of process optimization in the mining industry. We are also joined by a special guest speaker, Johannes Sikstrom from Boliden, based in Sweden. He talks about their two recent projects on first using a digital twin to evaluate advanced process control under multiple operating scenarios on one of their grinding circuits. And then secondly, the on-site implementation of advanced process control and the observed benefits. So mining is a harsh, changing and challenging environment to optimize. So how can technologies like advanced process control be used to add value? Boliden have collaborated with ABB in such an approach to target the optimization of their grinding circuits in Sweden. So I'll start with just going over the basics of advanced process control. In essence, an autopilot for driving the plant to an optimum operating state. So with advanced process control, it's seen as a secondary level solution that resides on top of the plant's control system, whether that's a DCS or PLC. So the advanced process control, APC is an umbrella term in industry which comprises of several technologies, model predictive control, fuzzy logic, inferentials used to predict states in the process. I'll talk about these in the following slide. So basically an autopilot that manipulates actuators and PID loops in the control system to first stabilize the process. Once the process is stabilized, then shift this process either higher or lower based on the economic optimum for process optimization. So if this is density or particle size, we're looking at stabilizing and then shifting it, if it's density, normally closer to an operating upper limit in a mill to minimize steel-on-steel contact, as an example. When it comes to the different technologies for advanced process control, one of the most common ones would be model predictive control. So MPC is using the dynamic models obtained empirically from process data and using the current state and historic states to predict the future of a particular variable, such as oxygen, pressure, grind size, etc., and then how far away that prediction is away from target, and then what control actions are required to drive it closer to reduce the delta between target and current value. MPC is very good at tackling units with challenging dynamics, whether it's systems with large delays or high complexity of interactions with multiple inputs and outputs. Fuzzy logic is a tool commonly used as well in industry, especially in mining. It's been around for a couple of decades now. It's more of a rule-based approach, more easier to understand from an operator perspective, but becomes a bit more challenging when it comes to tuning units with challenging dynamics. And then you have the ability to introduce inferentials into your advanced process control setup, where inferentials are predicting and inferring states of the process in between updates. So these states are normally infrequently measured, such as particle size, if it's manually sampled, or density. So with inferentials, you can use machine learning to predict in between based on online process data what those current states would be, and then you can introduce that into your control optimization with APC to drive that state closer to your target, and then receive your update from the lab, and then add that as a bias to your inferential prediction. There's also the ability to integrate with an information management system such as Knowledge Manager for continuing monitoring of KPIs related to the APC application. And this is normally quite handy when you would like a bird's eye view of the overall health of your APC applications and to gauge whether or not operators are using them effectively. So one of the challenges when it comes to optimizing minerals processing units, more specifically grinding optimization, would be the instrumentation element. So the ability to connect any new device, giving additional information on the process, is critical for progression towards autonomous mining optimization. The idea being that the more eyes we have on the circuit, the easier it will be to drive it to an optimum. So with grinding, one example could be cascade monitoring, which helps to answer questions such as what's my current shoulder and toe angles within the mill? Am I operating at maximum grinding efficiency? And are my current states causing excess line wear within the mill? So a solution that provides this information as an additional variables can be used and included inside of an advanced process control application. So when it comes to mining optimization, ABB's been leveraging advanced process control type technologies to improve operations from the mine through to the port. If we start at the mine, ventilation on demand, that's utilizing model predictive control to optimize the airflows underground to ultimately reduce energy consumption, as the airflows underground are quite highly non-linear, very much interacting depending on the level underground, as well as slow and complex dynamics. When we move to the concentrator, we have minerals applications such as grinding, looking to maximize throughputs and minimize specific energy. Flotation, looking to maximize recovery and minimize reagents. And then with thickeners and clarification, looking to stabilize the bed mass and the underflow density, whether that underflow density is through to leaching or through to additional fine milling. The underflow density plays an important part, and if that's varying significantly, then your downstream processes will be performing suboptimally. And ABB's advanced process control is even applied in the marine ports with their piloting systems to assist with collision avoidance. And MPC is seen as an essential component of autonomous shipping. Just quickly, when it comes to flotation, to give an example of how advanced process control is being applied. Typically, your main manipulated variables are going to be your reagent dosaging points, such as your collectors, your frothers, your levels within the cells, and your airflows being the most important in terms of quick dynamics for making sure that your cells are more or less stable and that you are not pulling too hard or pulling too softly. So with those as your main handles, the flotation application is receiving the XRF, typically measurements of the grades of the tails, concentrates, and typically the feeds to the circuit. And then understanding how far away we are from the lower acceptable limit for concentrate grade. Am I able to potentially maximize the use of my free handles, such as level and airs? And is there scope to reduce my cost of running that unit, which would be your reagents? Can I potentially reduce those whilst maintaining my targets for grade? And by applying advanced process control to flotation, typically benefits would be 1 to 2% increase in recovery, whilst at the same time reducing the specific consumption of your xanthates, your frothers, etc. by 10, 20, 30% in some cases. Another application would be the clarification or thickeners. So thickeners have very slow dynamics, where MPC is very good at handling these types of challenges, as opposed to a human operator with a shorter time frame for, let's say, attention or concentration. So MPCs can be applied here fairly well, looking at utilizing the handles such as flocculant dosing and your underflow drive of your pump, with goals of reducing your overdosing of flocculant, maintaining stable underflow density to your downstream units, and potentially reducing the wear on the rake within the thickener. So moving on, we are joined by Johannes Sekstrom from Boliden. Johannes is Head of Section Process Control and Analysis at Boliden System Technology, and was heavily involved with both the digital twin evaluation of advanced process control and the on-site implementation of the advanced process control projects. So he will discuss both the projects and why they chose advanced process control for increasing grinding performance. This is pre-recorded, so he will jump right into it. Thank you, Johannes.
I will talk today about a series of projects that we have done together with ABB regarding advanced process control. First, we investigated how we can motivate investment in these kinds of technologies, and then we also implemented it, but I will get into that. Yeah, so the first step of this series of projects was really in proving the technology. It's like proving that APC and advanced process control can bring value to Boliden's processes. And this was done with simulations. So digital twin is, of course, a buzzword that has been around for a couple of years now. But in this case, we had a simulation model describing the process of grinding in one of our sites. It's a fairly well-developed model. It's validated against site data. And it describes the whole circuit with the mills and the classifiers and stuff like that. And the reason that we wanted to try working with these kinds of tools is that we can do a lot more testing without disturbing production. And we can do a lot more severe cases with stopping things and stuff like that when we don't have to consider a real production facility in the background. We could also do a lot faster testing, of course. And all of this we wanted to investigate if it was possible to work like that, and what benefits we could get from that. An important part to consider when you use these kinds of simulation models is that the model needs to be up to date, and it needs to be a current representation of your process. Process plants tend to change a lot. You might have equipment being replaced and specs being changed and rebuilds and stuff like that. So you need to make sure that your model is currently representing the state of your process in your site, which can be tricky, but it can be done. Yeah, so if we sort of line it up here, we have the problem that we wanted to show before we implemented that there would be value in an APC solution for Boliden and the grinding in specifically. And we had a pretty complex control strategy already built on regular PI controllers, like traditional control, that we wanted to benchmark against. And we wanted to do this without disturbing the production then. And the solution is what I talked about in the beginning here, to use a simulation model and to set up a clone of the current DCS environment, our 800XA system. So we did a copy from the plant. That way we got every detail of the current control, all the nuances and extra stuff in there. And then we hooked up the simulation model to act as the process. So from the DCS point of view, it thinks it's the real process, but it's really a simulation model feeding those values. And then we could, in the same lab environment hosted by ABB, we set up also the APC controller. So then we could just switch between them and run the process over and over again. Yeah, and I mean, the benefit of this approach was, of course, the things I've already mentioned, with getting a good appreciation for how much value this would potentially bring, and being able to say quite certainly in what cases it would do better or be on par with the current control. And this is just a picture of the model. So on the left, you have just the process layout, and on the right, we have the model, which is done in Dymola, which is a modeling tool. And it's difficult to see in this overview, but each of these objects here all represent the equipment in the plant. And inside of these are then the models, the equations, everything describing how that part of the plant works. So like here's the mill. In there, we will have some models for the breakage and how that relates to the power consumption and so on. And we also have a lot of communication interfaces here then, so that it is able to communicate with the DCS clone that we set up in the ABB lab. So once we had that whole environment set up, we could really get into the nitty-gritty details. So we set up a couple of scenarios, quite a lot. We had around 10 scenarios in total, which we pre-programmed in the lab environment then for things to happen in a certain order. So and in this case, since it's a model, we can also change the ore properties, the hardness of the ore and stuff like that, which is very convenient for testing. But also, of course, things in the control. So we could say that there's a feed limitation for a period, perhaps, and see how both controls can manage that. And the beautiful thing of doing these scenarios is that we can repeat them over and over again. So we could run the scenario for the regular control, and then we could run it for the APC, and then we could see, okay, well, the APC is better, but we maybe still can improve it a bit. So we could tune it a bit against against the simulation model, and that way have a really good starting point for the APC model once we moved to site. But there's quite a lot of work here with going through the scenarios and tuning everything. And yeah, like these scenarios could run between 4 and 11 hours. And we only looked in the comparison at the hours after 2 hours had passed in the beginning, so that it wouldn't be affected by something that had happened prior to that scenario starting. And in most of our minds, and definitely in the one that we used here, we want to maximize the torque in the mill. And that's because the mill is designed to be the bottleneck of the entire process, because that's a very expensive equipment. So if we can use the mill better, then we can have a higher production for the entire facility. So we want to really use all of the installed power in those mills to be able to have a good liberation, a high recovery, and a high throughput, of course. Because you can, of course, maximize torque in many different ways. You could run at a very low speed and with a high load, and that would also give a high torque. But of course, we also want the high production, not only a good liberation. So we want them both. So we want to maximize torque, but by prioritizing a high feed and high throughput. And so this was the main focus of these scenarios in the benchmark. And a major limitation that is sort of inherent to the PID controller is this lack of cross-correlation management. In the example here, we have a torque controller and a load controller, which both controls the torque controller controls the feed, while the load controller controls the speed. But changing both the speed and the speed will also affect the other controllers' input. And this causes a lot of issues if you have the set points close together, because then these will interfere with each other and start messing around with each other. And due to this, you need to set points for these controllers with a difference between them. And this is like a gap which we can't really then get the performance out of. With an APC knows about both the torque and the load and a lot of other stuff at the same time, and can balance them all at the same time to the optimum, instead of this interactions being a problem. So this is like one of the main reasons that we saw that, because our PID strategy is quite good performing already, but due to these limitations in the technology itself, we were not able to really get that last performance. So that's one of the main reasons of why we were interested in going to an advanced process control. But now we're gonna look at a bit from these scenarios that I talked about earlier and see how it behaved. So there's a lot of trends here, but the dotted lines are the PID strategy, so the old control, and the solid lines are from the APC. And in this case, we changed the hardness of the ore. First, we made it a bit harder. You can see it's this red line here on top. It gets harder, and then the ore gets really soft pretty fast in this region. And we can see then that the PID strategy or controller, it loses the torque here. It's not able to maintain the torque because this easily grind ore, the feed is not enough to maintain a high torque. So we lose the torque. What the APC does is it lowers the speed so it can maintain a high load through this period. And you can see the solid blue here is the torque for the APC, which is kept really high, even though we have a softer ore. So, and this is sort of exactly what we were after. And here we can see in the benchmark that it works like we hoped, let's say. And one more case showing the same benefit really is we have a period here in the middle where the feed is limited for some reason. That happens. So we are down here at a really low feed, and then the torque, the dashed blue in this top lane, is really low for the PID. But for the APC, we can see that it reduces the speed quite fast and is able to maintain a higher load and thereby a higher torque. So here we can see that we have almost the same torque as we had with the high throughput. So here we really use that installed power in a good way. We get the better liberation since there is less ore, but we still use all the power, and then that results in a better grind and potentially a better recovery then. So this whole area between these blue lines here is sort of increased performance that we're seeing. And I'm not going to go through all of these scenarios, but you get the idea. There were some scenarios like if we had a short stop of like 5 to 10 minutes. In that case, the APC was pretty similar to the PID. It wasn't better, but it wasn't worse. So, but these were the big ones where we saw that it could really use more of the installed power. And so in summary, we saw that it could handle the cross correlation of variables and better utilize the torque. We also saw that it had a bit higher throughput because it was a bit faster to get the throughput back up after it had been reduced. And the last point here is quite important as well, because in a PID, you typically don't have any constraints management. The PID doesn't know about constraints. It only knows about the value, the set point, and how far it's between them. But since in an APC, you can be aware of the constraints and you can act really aggressively once you are close to an important constraint. And through that, we saw that we could potentially have a higher set point in normal operation because the disturbance reaction was a bit stronger to act once it was really needed. So we were really happy with this and presented it to our sites, and Garpenberg, one of our sites in Sweden, in the south part of Sweden, was interested in moving forward with the implementation, which we then did. And Garpenberg there has been mining there for a really, really long time, from 400 before characterized. So it's an old mining region, and it's a mixed ore, but the main value comes from zinc and silver. And they have a grinding circuit with 2 AG mills, one 5 megawatt primary mill and one 2.5 secondary mill. And like I said before, the ultimate goal is to maximize the liberation, to have a good recovery. And we do that by having a high power utilization. But we want to achieve that utilization through a high feed or high throughput, of course. Stability downstream, so the stability in flotation, is also a very important part in this. And we know that MPC have this predictive capability to look ahead, and that can bring additional stability because it doesn't need to violently react, but it can predict and think ahead a bit, which is good. And of course, constraints both on the torque, load, and some other constraints. What we're manipulating is the set point for the feed, and then the speed of both the primary and the secondary mill. We also have a pebble gate which feeds pebbles to the secondary mill, but that is currently operating at 100% almost all the time. So it's not really something we control that much. But if the torque gets too high, the gate can be stopped or reduced. But we actually left that to the normal PID controller. So that was not included in the APC because there really was no need. But we were controlling the torque and the load of both mills, and we also have size distribution measurements for what is going to flotation that we are interested in keeping in a certain range due to the paste backfill production. They have some quality demands there that we have some rules that go in and give us a bit of help to maintain that range. So what did we end up building then? It became a bit of a hybrid in the end. It was very difficult to get everything into a single MPC control model. Particularly the speed was difficult to describe fully in a linear model. So we have a MPC part covering the feed to torque relation, and then we have some fuzzy logic for the speed part. We also built a load target adaptation, we call it that, but it's basically something that continuously calculates what the load target should be and adapts that over time. And that's really to get a good stable process. If the load target were to go all over the place, that could cause some disturbances. So we wanted it to be really stable and slowly going where it needs to go to not introduce any issues for flotation. But that's the load target adaptation has worked really well. So, and of course, we have a lot of like checks and controls on everything. So we have ready states for stuff that needs to be in the right mode for it to be able to run. We also had some watchdogs on the communication and stuff like that, so that in case the machine where the APC is run is down, then it would detect that and be kicked back to the regular controllers until the machine can be restarted, or if there is an issue or something like that. And there is also some checks on the actual signal. So even if we have communication, we can have a dead signal for some reason, and we have detections on that as well. When we started the on-site implementation, we had a pretty good model already from the R&D project where we did with the simulation model. So we had a pretty good starting point, but still, of course, needs to be tuned. So we had a lot of step tests that we did on site. You can see them here. It's these lanes. So it's like 15 or so different occasions where we had step tests that could be used. So based on that, we further refined this model we had from the simulation. And then in the end, when we were on site to do the actual implementation, then we did the real fine tuning in the end to set up the final state. And to the right here, you can see just an example of the step response in load and torque to a step in the feed. And I mean, this is a really nice step response. So it's quite easy to see that this could be well described in the MPC for the feed part. Which was good, of course. Typically in Boliden, it's quite important to the operator to have most of their interactions inside of 800XA. So we don't like to have them into a lot of different interfaces, but rather try to pull stuff into the DCS. And this is the operator view for the mill control. And what we did was to do some communication variables between the set points and the settings that they normally set for the regular control that we had before. And then we pull those into the APC, so they are used there as well. And I think this was really good for making it an easier transition for the operators. So because they are familiar with this way of working, with setting the parameters here and to see what's going on. So this made it a smaller step for them to change to using the APC, because I mean, they are curious. They want to understand how it works. How do we interact with it? And I think that was a bit of a success factor, that we were able to do a very small change in the way they work. But the change was more in the controller, which they don't really see. We also have this up here, this APC box where you can see that it is on or off. We have here are some checks like the watchdog and if it's ready. And we also have some visualizations put into the image. I don't know if it's a bit small here, but here it says APC is controlling, and then it shows which controllers it is acting on and so on. So it should be quite clear to the operator what is going on. And here in this red box, we had sort of the main set points that they work with. So we were quite happy with this. It was a bit tricky to get everything to be integrated, but well worth the work, I think, for us at least. And so what were the benefits that we have been seeing for this? This has been running in production now for, a year or so, I would say now. And we have been seeing this better utilization of installed power that we talked about basically all the way through my presentation here, because that's the main thing we wanted, and we have seen that. It can use the speed of the mill in the entire range of the process and the production, so to say, to keep the load high, even if there is a limited amount of ore for some reason. So we have seen a higher power utilization. And an additional thing that we didn't really have as a main goal in the beginning, but we have noticed later, is that we can have higher throughput for longer periods, also due to the ability to control the speed. So if the feed is maxed out against the limit for how much feed we can provide, then the old control, so to say, that would use the feed. If there was a peak in the torque, it would reduce the feed to get the torque down. But now in this case, the control can use the speed instead. And that way we can maintain that high feed for longer periods of time without needing to reduce it. So we have seen an increased ability to keep a high throughput as well. And we have actually during this time now had a couple of like daily production records in tons in Garpenberg, which is really great. Of course, there's a lot of improvement work in different fields and different areas that have contributed to those record days, but I'm quite certain that the APC control is part of that solution as well, which is really good. We have not conducted any like real on-off tests, so we haven't been able to do a proper evaluation, like statistically significantly say how much better it is, but the indications, all the indications are that we have had these increases when we have looked over longer periods, which is good. And right now we are in the phase, a pretty critical phase in an APC project is where you have implemented it and you want to govern it and maintain it over time to make sure that it continues to deliver that value that we want. And we have worked a lot together with ABB during the last year, both in some small updates and improvements that has come up with things, but also in how should we work with maintaining this and who should be responsible for that the model is up to date. How should the communication work, stuff like that. So we're working with that now, which is very interesting. So hopefully we'll get set up something so that this can continue to deliver value over a long period of time. That's at least our goal. And yeah, so I think that's it for me. Thanks for listening, and I'll pass back to Ryan. Thank you.
Thanks, Johannes. Very much appreciated overview of those two projects. So in closing, advanced process control is a powerful tool for increasing processing performance on most major units on mining concentrators. It is a proven technology and is capable of handling multiple operating scenarios. And like most technologies, ongoing maintenance is critical. So having on-site champions or trained operators is critical for sustaining the benefits. And APC can significantly reduce operator workload for maintaining units close to operating constraints, allowing them to focus on other tasks. So thanks for attending today's call, and we will now close out the webinar. Thank you. Attending. Unfortunately, Johannes Sixtrom is unable to be here for the live Q&A. However, I'm joined by Robert Brown, the Portfolio Manager for Process Performance here at ABB. So I'll do my best to answer some of the questions that I see in the chat. The first one that I see is, what is your strategy for advanced process control implementation for greenfield projects, and is it different from the strategy for brownfield projects? So the difference between brownfield projects and greenfield projects from an APC perspective is we have less influence with brownfield projects on the recommended or required instrumentation. So the strategy with greenfield would be that
it's always important to include advanced process control planning from the start, and that mainly ensures that we are involved in the instrumentation, whether it's traditional instruments with grinding, flotation, etc., or some of the more smart instruments that are available today, whether that's image analysis or vibration or acoustic measurements within comminution. So that plays a bit of a role in defining the scope for the APC applications.
Brian, if I might add to that, is that in this particular case, we were using a digital twin to develop the control strategy. And once you look at these greenfield kind of setups, and in this modern world that simulation models and this approach of design by means of simulation is becoming more popular. So in this particular project, this allowed us to really develop the control strategy offline almost completely. And we had proper models before going to site and commissioning. So I believe definitely this is also becoming more of a possible approach in the current times, is that with these greenfield projects, we can use a simulation environment, develop a control strategy, and this would allow us to ramp up much quicker once the plant is actually online and in production.
Fantastic. Thanks, Robbie, for your 2 cents. Is there any prediction model for quality parameter? So in this case, quality parameters with comminution is normally around the density achieved, the particle size, or the liberation achieved. For this particular plant in digital twin, so 2 plants, both had particle size analysis. And density. If the plant does not have this instrumentation, there is the possibility to build prediction models using inferential modeling platforms such as IMP. So there's certainly the ability to include quality estimations within the control variable list. I don't know if you want to add anything to that, Robert.
Yeah, I think that is pretty solid, Brian, is that we have some soft sensor technology that helps us to estimate parameters that cannot be necessarily measured online. This is quite common. Definitely, if you look at like cyclone overflow, particle size in the grinding stage, we can build some AI ML models to have this available online that can be used in control and in flotation and the other areas. We also know that lab measurements still play a key role in the optimization initiatives when it comes to APC.
Mm-hmm. There's a question, how do you manage bad data? For 2 parts of APC, the offline parts, so the building of your application and modeling. So for that part, the modeling, it would be a mix of manual and data pre-processing, and that can be done inside of the model builder when you are cutting bad data or selecting only parts of the process that you know are representative of normal operation. Online, you have the ability with input processing inside the application, as well as the possibility to do sensor validation with some other tools. So we mentioned briefly before inferential modeling platform, and there you can also do sensor validation. So making sure the instrument that you're reading is in an expected band and is not playing up. If it is playing up, marked as bad, and you also have the ability to have a estimation of what the state should be, and that could be fed into the APC application to allow it to continue to optimize to that point until it's recalibrated and brought back into proper service. I think there's one more from Paulo Lopez. How long does it take a digital twin project, and how long to implement digital twin? What are the key stages to the project?
Yeah, so Ryan, I think as I was quite closely involved in working there as well with the Boliden team, if I would say the stages that are needed is, okay, first you need to build the model, the simulation model or digital twin model. So that's definitely the first part. And depending on the scale, that can take a couple of months. In this case, it was the grinding unit. So I would say that we take around 1 to 3 months, could be a realistic kind of timeline. And then, you need to do some model validation. This could also take some time, maybe just a couple of weeks if the model validation comes back as good. Otherwise, you need to go back to the modeling phase, adapt the models, and make it again more realistic to match the data. And then what follows thereafter is, okay, so what is it? Why did we build this digital twin model? What is the aim of it? So then it becomes, are we doing this to do some bottleneck identification? Are we doing it to build our APC strategy? Then you can use this model to ask these questions and get feedback. And this is up to what the real need of this model is. It was really awesome for us to have this model platform where we connected it even straight to the DCS environment. It was a real mimic of the automation system. So it allowed us this front to back evaluation of what can we change in the control system, what can we adapt in the control philosophy in the APC, and then what is the added benefit and the motivation, the business case then of going forward to implement this. And we actually did go and implement this on site. And as you heard from Johannes, that the results was very positive.
Thank you, Robbie. I don't see any other questions. So this webinar will also be on demand. So if you would like to share that within your organization, please feel free. And I just want to thank again Johannes for his time and efforts in the projects and his time for helping create this webinar. And thank you, Robert, for also joining. Thanks all the listeners, and we will close this webinar out. Thanks a lot. Goodbye.
Cheers.